So in this video, we're going to take a look at enthalpy, and enthalpy is usually written out using the variable h, or the letter h. So we have U or E for internal energy. These are really the same thing, and then we have the Gibbs free energy, noted as G, which we looked at earlier. The h, this h thing, enthalpy, is another function that appears to be derived by Josiah Willard Gibbs. At least he gives an expression for h in his classic paper published in the 1870s. And again, we can do the same thing with G. With G, we write three equal signs because we define what G is. We said G is equal to the internal energy, which we'll write as U, plus P times V minus T times S. Well, what Josiah Willard Gibbs did is he made up another function H. He didn't use the term enthalpy. That's the term we're using now. And he didn't use the letter H either. But this is really the form. Again, we're going to draw three lines because we're going to make up this new function. And he set it as U plus P times V. So notice that it is very close to the Gibbs free energy, just we're dropping this term here. Let's erase the chalkboard and just look at it in isolation. So enthalpy is H, which is equal to U plus PV. So now we're going to do a little bit of calculus in differential form. dH is equal to du plus pdv plus vdp. And you might remember that du is equal to tds minus strike that, pdv. So we're using the engineering convention where we're going to use a minus sign. This is PDV work. It's work done by the system that decreases the internal energy. And by taking that engineering convention, this drops out with this, and we're left with DH equals TDS plus VDP. Well, why is this so handy? Let's erase the chalkboard and look at it again. So DH is equal to TDS plus VDP. So what happens if we have constant pressure? If we have constant pressure, that means a delta P, or in this case a dP, are equal to 0. There's no change. So this thing goes to 0, which knocks out that whole term. And you might remember from an earlier video, this is equal to dQ. So dH is another way of forming, of calculating or describing something called heat, or usually written as Q. And so dH can be thought of heat at constant pressure. And we do a lot of experiments at constant pressure. It's easy to do an experiment in the lab where we take a beaker of some kind of stuff, and then we, let's say, fill it up with some kind of solution, then drop some little fellows in it, some kind of crystals, watch them dissolve. So we end up with a beaker with just a solution and dissolved solids. And we can look at the heat of dissolution. We could do the same thing by melting things. And when we do these things where the pressure, atmospheric pressure in this case, is constant, then we can talk about the amount of heat that is released and describe it as this thing H, or as enthalpy. So you can think of enthalpy as a form of heat so long as pressure is constant. What if pressure is not constant? Then we have another energy term, an energy term that would be minimized at equilibrium when, let's rewrite this again, so dH is equal to TDS plus VDP. It is an energy term that would be minimized when, it would go to 0 as entropy and pressure are held constant. So like our terms for our equations for Gibbs free energy, or U, or equivalently E for internal energy, this is another way of thinking about energy. And what are we going to hold constant? We have a system that is held at constant pressure, and somehow we were able to hold entropy constant. Then it's dH that is the energy that would have a value of 0 at equilibrium.